welcome everyone to this afternoon's session, which I'm very excited to be chairing. We've got 3 speakers lined up for you. The afternoon will start with a talk by Marija Vucelja from the University of Virginia, who will be telling us about anomalous thermal relaxation on dense graphs with Metropolis-Hastings dynamics. Please.
Thank you very much. I want to thank the organizers for inviting me to be a part of this program. I visited in July. I learned about self-interacting processes and gave a talk actually about a similar subject. For those of you that were in the talk, there will be some repetition, but there will be a different angle and some new things. And I'm also thankful for organizers whom I know some, sort of like, especially Joris and Sam, and sort of to introducing me to this wider community of mathematicians and statisticians. We all, I think we all like the same problems, me coming from physics, and that's why I want to talk to you about anomalous thermal relaxations. In fact, I'm changing the title a little bit. I promise there will be some Metropolis dynamics on dense graphs towards the end, but that's not the, maybe, at least in my view, the most exciting part. The most exciting part for me is the potential applications of this kind of unusual thermal relaxations for efficient sampling. So this is not something that I have an answer for how to use it for efficient sampling. Rather, it's an invitation for a discussion. I'm here until the end of this week, and I would love to see some sort of interdisciplinary kind of, at least discussions, if not collaborations. So, all right, so what I do is non-equilibrium statistical physics and its applications. Lately, I've been focused on thermal clenches of physical systems. So I'll tell you what I mean by this, and most of the talk will be about anomalous thermal relaxations. But I also like to think about algorithms and about sampling, in particular Markov chain Monte Carlo. So, many of you have heard me already talk about Markov chain Monte Carlo, in which you break detail balance and kind of enlarge a phase space in order to sample more efficiently. And rather than telling you the same story many times, I want to tell you something new that's, and while I'm trying to still figure out the bridge and the connection between these 2 new things. Since this work that was inspired by works of Ken, Pak, and Lovash, and Diakonix, Holmes, and Niels, and I had numerous discussions with Werner Kraut on this. With my student, we also applied a type of an irreversible Markov chain Monte Carlo to a self-avoiding walk. Essentially, we modified the Beretti-Sokal algorithm. Now, Beretti-Sokal had sort of the irreversible version of the Beretti-Sokal algorithm, and we had some improvement in 2D and in 3D. And if you want to talk to me about this was a while ago. I'm happy to go over that too. So that's both of these are in some sense even more aligned with the topic of this conference, because it's kind of beyond diffusion. And whenever you break detail, often when you break detail balance, what you do is, sorry, I'm figuring out this pointer. It's not my pointer, but I'll get the hang of it hopefully. So when you enlarge the phase space, you kind of break detail balance, and you do create some flows, so it can be viewed as inertia biasing your otherwise kind of like just diffusive behavior on a space of states. I should say my jargon is a physics jargon, my notation is a physics notation, and I don't have any particular target slide to reach. So whenever you don't understand me, please just interrupt me. I'm happy to get one point across clearly rather than 10 sort of, and leave you all sort of among the first slides. Okay, so in this endeavor of anomalous thermal relaxations, I'm helped with lovely collaborators and with some students. So my students, Matthew Walker and Saikat Bera, and then now I've joined with Jin Chen, an excellent undergraduates, Alexa and Himani. Himani just started, of course, supported by NSF. And so for the last, almost a year, we've been writing this report. It's finally finished. The editors are on our tail about anomalous thermal relaxations, and it's quite exciting, and it's supposed to be readable for a broader physics audience, physics, and anybody who's interested, certainly mathematicians and so statisticians. The report's title is something about speed up with now I'm paraphrasing sort of with non-equilibrium statistical physics, roughly. But it's these kind of shortcuts that are induced by anomalous thermal relaxations. And so besides being interesting for fundamental statistical physics and all sorts of optimal heating and cooling protocols, I think that the two areas that I'm interested in overlap, and that and what I want is to inspire a discussion on the cross section. And I see that this pointer is going to give me troubles, and kind of like potential applications. Okay, so what are anomalous thermal relaxations? So here's a prime example. It's with water. So bear with me, I haven't solved why it happens in water, but it's a very old problem. That was observed by none other than Aristotle first. So Aristotle said that when you put water in the sun, it will cool faster. Then Francis Bacon says, well, slightly tepid water freezes more easily than that's utterly cold. Then René Descartes says that you have soluble particles that kind of like evaporate when the water is being first heated, and then therefore it cools down more efficiently. And finally, the person whose name, the effect is named after him, Erasto Bartolomeo Mpemba, he was in the business of making ice cream. And what he did was first observe it with making ice cream with sugary milk, and then repeated an experiment with water. So what was the experiment? The experiment was you take a beaker. Well, okay, the original was you take an ice cube tray, fill it with sugar and milk, and put it in the freezer. And he put lukewarm milk, while the others put cold milk, and his froze faster. So then later with Dennis Osborne, they measured it, and they measured that they measured with they put water in a beaker, nicely insulated it from the bottom, put it in a freezer, and they saw that there are conditions under which the beaker prepared at a hot temperature cooled down faster than the one at a cold temperature. So, inspired by Mpemba's water experiments, you can define a Gedanken experiment first, kind of like just to see how to think about it at all. All right? So, suppose you have a system and you prepare it at a hot temperature, and you have another system identical to the first one that you prepared at a warm temperature. And you do this twice, but under identical conditions. You take the hot one, put it in a freezer, put it in your cold environment, and let it cool down. And then, if in an ideal world you can do it sort of again, same coupling to the environment, and let it cool down. So in a numerical simulation, you can certainly do it. And you ask, all right, my system started from thermal equilibrium. It had the Boltzmann measure, if you want, characterized by T hot. And now this probability distribution is evolving in this high-dimensional space in which it lives. And as it's evolving, it wants to reach a kind of like this other point denotes the Boltzmann distribution at the bath temperature. And you ask who gets there faster. we clearly both are constrained to only walk on this isolocus of equilibrium points. The one that started off closer wins. So quasi-static in this sense is boring, because quasi-static means that you kind of are constrained to live on this line. If you made an experiment, quasi-static would mean that you lower the environment a little bit, your system catches up. You lower it again a little bit, your system catches up. And it kind of always stays close to equilibrium or at equilibrium. Okay? While as if you shock your system, then kind of you prepared it at a hot temperature, but now you insert it into this cold environment. You're allowing it in general, you're driving it out of equilibrium, you're allowing it to be anywhere in this probability distribution space, so it doesn't have to, so basically while here you had an equilibrium distribution at a particular temperature, temperature is not defined anywhere except at t equals to 0 and t equals to infinity. And then you ask the same question, all right? So who arrives to the vicinity of this bath temperature faster? So now the warm system has an advantage. It started off closer, but does it get there faster? So events in which there is a kind of like a switch of the labels, the system that started off further away, the hot system, overtakes the warm system. That's what we call the Mpemba effect. Okay, so I'm speaking a lot about cooling. I can speak also about heating in the same way. It's just easier to stick with an example and talk about cooling. All of this is valid also for heating. You can ask about efficient heating strategies which evolve sort of starting from a lower temperature kind of. And some of it has been also, and this thing, the Mpemba effect has been both proposed and seen also, and then it's typically, if you look at the literature, it's called the inverse Mpemba effect. All right? So what I'm talking about is, if you like more to think about observables, if you had some observable and it had its equilibrium locus here, quasi-static evolution would make it, let's say it's your magnetization of your spin system. So this would mean if you are on this line, you always have a magnetization which is well defined and correspond to some equilibrium average. Now, here I want to explore, I'm going off of the beaten path, out of equilibrium, and this would be the average of that observable with respect to the current probability distribution function. Okay? And so this is just to say, sort of, we are excited, we are writing this review and hoping that it will kind of both introduce this effect to other branches of physics and inspire work in related disciplines. Okay, so how about observations? So I already told you about water, clatrite hydrates. So some would say, well, this is almost like water. Chemists would say, no, like it's distinct, but it both have hydrogen bonds. It's similar, sort of granular fluids, colloids in optical lattices, polymers, qubits, magnetic alloys. And the numeric list is even longer. As you can imagine, you can play these games and, for example, how things relax, degrees of how excited are different degrees of freedom is important. So in physics, we have this notion of equipartition, meaning that each degree of freedom contributes, each excited degree of freedom contributes equally, kBt over 2 more precisely. So if you break equipartition, so let's say translational degrees of freedom relax faster than rotational degrees of freedom, then you can even more easily enable these kind of things to happen. All right. But let me tell you how to think about the Mpemba effect. So let me stop. Are there any questions so far? All right. If there are, just interrupt me, please. So let's think about the general physical system. I apologize. I have I have considered yesterday changing the notation to the more math conventional notation. Please do not cringe that my probability vector is a column vector, and just play along with it, okay? Physicists typically tend to write it this way. So this is my, this is a kind of a general description. This is a master equation. I have a relaxation matrix. It can be a matrix or an operator, depending. I want to think about a continuous setting, or I want to think about a discrete setting. In fact, I want to talk to. I was intrigued by the talk of Gabrielle, because we worked a lot on the overdamped Langevin equation, and sort of played similar games with anomalous thermal relaxation. So there, the role of this relaxation rate matrix is the Fokker-Planck operator. So so maybe at some just so something for later. So suppose this is a master equation, and P is the probability of your system to be at a particular phase space point at time t, and then R is your relaxation rate matrix. There is a stationary a probability distribution. It's the Boltzmann distribution, and for the rest of the talk, K Boltzmann will be 1. And I have detailed balance, and detailed balance just is a property of this equilibrium. It's a property around here. So then, so basically, it ensures that at a large time, my system indeed converges to converges to this Boltzmann distribution. And my initial condition, I choose it to be an equilibrium at another temperature. I don't have to have it equilibrium at another temperature. I can perfectly nicely play this game between non-equilibrium steady states, but just for the simplicity, so that I have a label where we know kind of like, you know, warm is closer to cold than hot, sort of just to have a label and a sense of distance. I'm choosing to start from another equilibrium. Okay? And now the details depend on your favorite system to think about. It can be the Liouville equation, the Fokker-Planck, the Lindblad equation, if you want to consider the evolution of a density matrix. So it doesn't really have to be, it can be kind of quantum, so if you want. So how to measure the effect? So you need some notion of are you close to your target distribution or not? And here we borrowed something that you guys use daily, the Kurbel-Kleiber divergence. It will do, and it is not the only way to measure. I can use L2 norm, for example. I can use total variation, but here I chose to just to exemplify with the Kurbel-Kleiber divergence, and it's nice to think about it this way, because at the end of the day, it can be rewritten as a total number of entropy produced at time t, and a total amount of entropy produced in equilibrium. And so basically, it's clear that I want to minimize this difference, all right? So what happens when I have a Mapemba effect, that means that something that was initially far away over time overtook something that was closer, and this is the time at which I have the Mapemba effect. And now I'm gonna kind of like tell you what are the hallmarks, what systems have it. If you like optimization, you can think about that in some sense this hot start is better, more optimal, if your end goal is to equilibrate at this low temperature. So, okay, yes?
So, sigma at affinity, isn't it 0? Like at equilibrium, it produces no entropy.
No, this is the entropy produced along this during this evolution,
okay,
sort of. It's summed over, sort of. Yes, of course, sort of. Your entropy is maximal. The production is 0. The derivative is 0. But this is summed over the evolution, sort of. Okay, I'm sorry. So the total amount of total is the magic word that I'm lacking. Yes. All right. So the one way to think about this is like an eigenvalue problem. So especially if this is this relaxation rate matrix, and in which you have both left and right eigen vectors, and the 0 corresponding to the target distribution. And this is so the lambda 2 is the spectral gap essentially, sort of. So they're all negative, but sort of. So the gap is minus lambda 2. That's your measure of the one of the measures of the relaxation time needed. And then when you write the solution of the probability kind of vector in terms of the eigenvectors and eigenvalues, so this is where you want to arrive, and these are the deviations due to the different relaxation modes. Now, these deviations, these are kind of projections, and the only thing that knows about the initial condition. So most of you here are interested sort of in reducing the spectral gap. Here, I will have a part on that too. I will be talking about a prefactor to the spectral gap, okay? So kind of finding an initial condition in which this prefactor is smaller, and therefore in finite time there is an overtake. So if you have a long time limit, so I need an assumption that I have a gap between lambda 2 and lambda 3. Then in this long time limit, I can forget everything except for the slowest eigenvector and eigenmode. And the typical behavior of this coefficient is like this, sort of. If I already started with the correct temperature, there's no cooling or heating, this deviation from equilibrium is 0. Because then all of this is, I'm at that equilibrium. At very, very large time, my Boltzmann distribution goes into a uniform distribution. Therefore, my overlap coefficient tends to a constant. So, and otherwise, as a function of the initial condition, it's a continuous function. So it looks something like this. It can be monotonic also, but monotonic is boring. Why is monotonic boring? Because if it's non-monotonic, then I can have a finite time at which the hot initial condition performs better than the warm, right? So the condition for the Mpemba effect is that this overlap coefficient is non-monotonic. You can ask me what's the simplest system. Give me a simplest system that can do this. The simplest system that can do this is a kind of 3 levels connected with with a relaxation rate matrix. So 3 energies and some coefficients, some rates between them. Unfortunately, it cannot be 2. Sort of, you need to have an equilibrium, a slow direction, and a fast direction. But with this, you can find a relaxation rate matrix pretty quickly that has that. Okay.
Excuse me. So this is the minimal model.
This is the minimal model. Okay.
And what can you show for this minimal model?
Oh, I can show many things for both the minimal model and I'll show you some other models, sort of.
And the rates, they are, let's say that we have a parameter which corresponds to temperature. Is that what you're saying?
Of course,
These
yes.
Rates,
so
these rates remain. These rates are detailed balanced, are reversible.
Yes. Sort of. So the rates I can parameterize like this. These are some barriers, and for a particular choice of barriers, I have Metropolis-Hastings. Sorry, Metropolis. This is I think max EJ. So yeah, you can. So all right. So let me show you. So this is where my friend Oren Raz visited me and told me about this Mpemba effect back in Virginia. And then I had lots of questions. Wait a minute, does it happen in a thermodynamic limit, or this is some sort of a finite size effect? It will be interesting also as a finite size effect, but yeah, this table has a finite number of molecules that it's composed of, but it's 10 to the 23. So for all practical purposes, it's in the thermodynamic limit. So many things of real world will kind of, if you want to emulate the real world, will require you to have a good thermodynamic limit. Then how often does it happen? Sort of, am I searching for a needle in a haystack, or I'm searching for something which happens with finite probability? This is important if you are thinking of some sort of application. So if you're thinking of, can I suggest to my fellow experimentalist that he should really search for this Mpemba effect or not? Intuition, when does it happen? Now, we have some intuition in very simple systems like the overdamped Langevin equation, like this kind of toy models, three-state system, some mean field antiferromagnet, and I'll walk you through some of it. Most of it I spoke about in July, so in order for Sam and a bunch of other people who were here in July, I will, so that it's not just a repetition, I will talk about a little bit about different emphasis on kind of like mention examples that I didn't mention back then, add the part about Metropolis dynamics, but really we are at the tip of the iceberg in understanding it in many systems of why it happens. All right. I should remember to pause once in a while to breathe and then look for questions. So, when we started to think about this, like with Oren, whom I heard the story from, and then Ori and Israel, so we thought, all right, is this all? I mean, great, you changed the prefactor a little bit, but so what? I mean, it's not an exponential speed up. Why do you care? So then it turned out that actually this constant here isn't sign definite, so it can cross zero many, many times. And then you can ask, so what does it mean that if I position myself where this coefficient is exactly zero? It means that you have managed to start from a position where your relaxation, where you don't have any projection on your slowest eigenvector. Now I understand if you know what your slowest eigenvector is, a lot of the job is already done, and there are many systems where we don't know, and I'll speak a little bit about that. That's the real challenge. But there is another challenge of when you do know the second eigenvector, or you can approximate it. So what does it mean? So it means that the relaxation time shortens from being defined by the slowest, by the first non-zero eigenvalue to the second one. So you have a jump in the relaxation time. Moreover, it means it's like spaghetti with ends. It has some topology in it, sort of. To know whether or not I had an odd number of zeros, all I need to do is I need to know the derivative here and the value of the constant there. So I can examine the ends and question whether I had a, I mean, by now I know how to search both for odd and even zeros, but let's say here it's very clear to see the derivative here times the constant there gives me that I at least had an odd number of zeros, okay, between t. So why is that good? Because we typically know how to do some limits, high temperature limit, low temperature limit, and finite temperatures you typically don't know how to do. So then, so this was this strong Mpemba effect, where there is a jump in the relaxation time, so relaxation exponentially faster because it's determined by lambda 3, and we predicted it, and then it was beautiful that it was, this is the only time it happened to me in my life that somebody then measured something that we predicted. I won't speak about this experiment. This experiment is though like diffusion. Maybe I should just even not say why I'm not speaking about it, just say that it's diffusion and we want to go beyond diffusion here. But I want to show you something that, so this is this jump that I'm telling you about in the relaxation time. There is a dip. This is not the Kullback-Leibler divergence, rather it's the L1 norm, but the Kullback-Leibler divergence will show you the same thing. Here's the control, here's the start from a hot temperature and start from a cold temperature. The two cross, as I told you, and this is a semi-log plot, sort of where you see that there is a straight line. The system itself, since I spent so much time on this slide, is a diffusion in a potential well. Sort of, it's done with optical tweezers. I'm happy to talk much more about this. I have worked on this sort of a lot. So, but here just this is a strong Mpemba effect hallmark, the dip in the relaxation time. So, okay, so does it happen in the thermodynamic limit? So here's something that's more similar. Here's a Monte Carlo. All right, well, first Monte Carlo, there will be several Monte Carlos in this talk. This Monte Carlo is a very easy one. I have an energy, so these are spins. They are divided into two groups. All of the guys in the blue group don't talk to each other. They only talk to the guys in the red group. The interaction is antisymmetric, meaning that the neighboring spins on this graph like to be misaligned, all right? So that you see from the interaction constant being smaller than 1, and it's in a magnetic field. Now, the way to describe this system is it has what physicists like to say 2 order parameters. It has magnetization and staggered magnetization. You can equally describe everything with a linear combination of the two, which is magnetization on one subgraph and magnetization on the other subgraph. What is magnetization? Magnetization is just a difference, a normalized difference of spin up minus the spin down, all right? So normalized with the total number of spins of that particular subgraph. And now you choose your dynamics. What I'm telling you doesn't work for every dynamics, but qualitatively it works for many in the same way. So here's what I see, okay? So this colorful graph is a phase space of the initial temperature versus the magnetic field. And this line here is a line saying where your system is an antiferromagnet and where is a paramagnet. So, okay, so antiferromagnet has a checkerboard, okay, pattern. Paramagnet, once you turn on a high enough magnetic field, sort of then they align with the field or something like that. So then what you see here when there is no colors, right, so this is 400 spins. If you are questioning how can we do 400 spins, it's because it's mean field, because I can describe it with the kind of total number of spins times 2 plus 1 states of magnetization. The matrix is much smaller that I need to simulate. There is a large degeneracy because it's a mean field. But the reason why we like it as a test bed is because it's the reason why I like it as a test bed is because I know everything about the system almost analytically. I know many things about it. So the colors mean I have a Mpemba effect. What Mpemba effect, that is a technical detail, kind of how many zeros do I have above the bath temperature, and it's not interesting to go into this right now, sort of. If you ask me, it's a very exciting thing, but kind of zooming out the big picture, what I want to show you is you get a kaleidonoscope like this, and you have interesting cases. You see that phase transition play a role. You can have it also if your temperatures are on the same side. What I did not say is this is like an existence graph, sort of. Where you have color, there you have some sort of an effect like that. You can ask how we managed to scan this from sort of, did we have to simulate all temperatures? That's an interesting question where the strong Mpemba effect starts to play, because remember the spaghetti where I hold the ends, sort of when I'm perturbing the ends based on the derivative of A2 and the value of A2, I can tell what kind of an effect I have, and also the fact that A2 is a continuous function. So that's also interesting of how we measure this. If you take the thermodynamic limit, so in this case, it means you instead of having your master equation, you write a kind of continuum limit. So now your magnetization changes continuously. You can solve this equation, and you can show that this probability distribution depends only on the two magnetizations. Doesn't depend on the full spin configuration, just depends on the two magnetizations. And now you can, on this space, this one is a nice graph also to understand. This blue line is the isolocus of all of the equilibria. And suppose I start from here, then the individual trajectories are I go, 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 I hit traffic. And I'm slowed down by the traffic. So this is the second eigenvector, sort of the line of the second eigenvector. Now, all of these trajectories suffer from that, except for one in this system. Sort of, if this is the path, then this trajectory has no projection on the slowest mode, and that's the strong Mpemba trajectory. Okay, so positioning your system in vicinity of it might be beneficial or useful. Especially, remember, it's like your Monte Carlo game. You don't care how you get there as long as you get there in a finite amount of time, and sort of your kind of like so that you can really start. Then you can measure. Then you can have realizations that are made from with that particular stationary measure, right? So this is so I'm telling you, sort of in the among these guys, sort of the best one is that one. Sort of it doesn't have any projection of the slow direction. So now I say all is fine, but you're talking about mean field. I usually don't have a mean field. I can have a system which is complicated, like a 2D Ising. So my friends did it. Amit Gal and Oren Raz did it, for example, for 2D Ising, 70 times 70 spins. So think about it. It has 2 to the 4,900 states and kind of Glauber dynamics. And there they looked at the magnetization and a staggered magnetization. So they had kind of like, it's a checker. Okay, so it's a system where you have two symmetrical sublattices. Okay, so this paper essentially talks about something a little bit different from what I'm trying to say right now. So they talk, but equally interesting thing for this community. It talks about, it compares two protocols. One protocol is you're just, you start your Glauber dynamics from here, go to Tmax, and then the question is, well, wait a minute, if I want to go to Tmax, is it better, I think it's about heating, okay? Is it better to go to Tmax like this, or or it's maybe better to cool first, and then, so this has some pre-cooling, kind of to cool first, to aim to reach this other temperature for a finite amount of time, and then heat. So this T0 temperature is in between the two. So it turns out that it's better to pre-cool in this particular case. But what I want to tell you is that beyond mean field also, you can linearize around the point where you want to get to, and you'll have a slow manifold like this. So this is where your approach along the V2 eigenvector is, and you'll have a fast manifold somewhere else. And so so basically by fixing the sort of, you have to be a little bit careful about the norm, but if your A2 coefficient changes, this coefficient changes sign sort of for two different starts, then you know that you're approaching it from two different directions. You can tell where the second eigenvector is. You can tell where the slow manifold is. So you can try to kind of like correct for that. And yes?
Sorry, here, when you say you cool down first, is it that you put a constant temperature in bath at some given temperature, or you have a time-dependent thing with this crazy stationary? I'm saying
that this flip operator has T-bath is T-max, and for a while, instead of being Tmax for time tau, I keep it to be T cold. So I'm kind of driving this system from one and the same point, but I'm telling him, no, I know I want you to hit, but now you're going to this other attractor for a while.
At that time, you kind of expect that you have reached the pipe of T cold. When you start back, you're going to Tmax?
No, No, I don't go all the way. No,
Okay, so
no,
you
for a
wait
part.
targeting cycle, but you wait before, you stop before.
I stopped before.
Okay. So
But
it's not exactly the theoretical, because before you always had initial conditions which were like equilibrium at some temperature and.
Right. So here I'm changing. Here I'm changing. I said like I know I want to get here, but I'm gonna hit slow traffic there. So therefore, let's go somewhere else. It might for a while, and then I will avoid the slow traffic because from there I can switch to the route, which is sorry for the colloquial language, but sort of that's what I mean.
But so just so that you understand, here when you say somewhere else, it's in terms of these variables M and S. And not really in terms of this T code.
MNS, in terms of MNS. So I need to know something. I need to know that in order to I cannot avoid knowing something about the system. I know that the relaxation of this system, although it's not mean field, if I relax the magnetization and the staggered magnetization, I'm gonna go pretty close to equilibrium. So I know that where I am roughly, sort of what are their equilibrium values. So I'm tracking several observables. Thank you, that's a great point. In a sense, the great point being that I cannot measure my whole probability distribution function. I can only measure several observables. And this is the sort of, I know nothing about the eigenvector. I know about the projection of these observables on that slow mode. Okay? So if they don't depend on V2, I have no chance, sort of. Random energy model, 7 minutes, 7 minutes to ending. Random energy model is a beautiful story where we managed to say something about the probability of how often do we expect to see this effect. For people that don't know what is a random energy model, it's I take a set of energies out of a probability distribution. I say this is my sample. It came from wanting to know about disorder systems, sort of. So you say like, okay, sort of, I have this many energy levels, and each sample has a different impurities, so I might as well take them random. It's kind of like the success of the random matrix theory in nuclear physics. When it works great. And it's also very rich. So a sample is a particular realization. This is my quench disorder, and then I take a rate matrix. Bij's are my barriers, and these barriers. So now I'm going to search for how often do I lower bound for the Mpemba effect. How often do I see the Mpemba effect? So I'm going to search for an odd number of zeros. How I'm going to search for it? Well, I already told you. I'm going to look at the sign of this derivative and the sign of the constant there. For, because we all like positive quantities, I'm going to put a minus sign and ask whether it is larger than 0. Okay, so we did that numerically. It's extremely simple to do this. We had a certain number of energy levels. We chose the energies to obey Gaussian statistics. We chose the barriers to be all positive, but kind of like a right-hand side of Gaussian. But then we did something which is maybe more interesting in this crowd because it's easy to do this numerically. We said, wait a minute. But in general, what I want is for a large matrix, I need to guess the second eigenvector. And I need to average it over the barrier statistics. Yeah, good luck. This is impossible, all right? So this is like an impossibly hard problem to solve. And when you are faced by an impossibly hard problem to solve, then we said, okay, sort of, let's do something different. And the different thing is, well, let's guess the second eigenvector. So now this guess is only good if I'm, okay. Frankly, to be honest, I don't know, I don't know to a satisfactory level, even for a physicist and not for a mathematician, when it's good. But I have a hunch why it's good and why to search for it this way. So I'm going to take a completely, remember, my barrier statistics is Gaussian. I'm going to take a vector with Gaussian entries. And I know that there is an orthogonal basis. My matrix obeys detailed balance. I can symmetrize it. There's an orthogonal basis. and this is written in this orthogonal basis. And I'm then in that orthogonal basis, my stationary, this is proportional to my stationary distribution, and I'm just going to make it orthogonal to that. My second eigenvector has to be orthogonal to that, okay? And the thing that's going to save the day, so that's not a good candidate for my barrier statistics. We did change that every candidate like this does create a bona fide. So I have a particular assembly of R matrices that I'm interested over averaging, okay? Any candidate I make this way does create a candidate from a bona fide relaxation rate matrix, but sort of, and then when you average, turns out the thing that I want to measure is independent on the fact that I have just switched an assembly. So instead of the random barrier assembly I started off, I have an assembly of these Fs, and I measure a particular quantity where the disorder, which is due to the energies, so it's a quench sample is in these U's and W's, and disorder, which is due to the barriers in this is in this X vector. It kind of decouples. Long story being short, because I see that I'm out of time, the lower bound for the Mpemba effect for this isotropic assembly, which I can do theory on, matches the random barrier assembly. Granted, the details matter a lot. The two assemblies are like comparing apples to oranges, but apples and oranges are to first approximation both fruit. So there, there is a region of the barrier statistics for wide enough barriers where the two assemblies give the same result. So this is very beautiful, and I want to work further on making it more precise when the two differ and when the two assemblies say different things. Now, Metropolis dynamics, as a promise in the last 2 minutes. So we solved, we had a complete graph, non-degenerate, these kind of energies, and we thought we found, Israel and me, we thought we found the spectra. Then I spoke to Percy Diaconis and says, no, this has been known since a long, long time ago. It's a very well-known paper, just in a different community. So I need to talk to more people that do statistics, because I have not found it on my own. So apparently the spectra was known, but we could tell by knowing the whole spectra that there is no effect on a complete graph. Then when you start off chipping off links from this graph, then you can induce, so I chipped off one link, and then I know the spectra again. If I chip off that link and I chip off another link, I also know the spectra exactly. So I know that I induce a weak effect, I induce a strong effect. Now the question is, how well can I do and which links to chip off? Then I don't know how to tell you. That will be much more interesting. That's something that I'm working on with the student. And surprisingly, I managed to reach the summary with a speed which is not ultrasonic. All right, so this is the summary that Mpemba is a general phenomenon, and I believe there are potential applications for efficient sampling, and look forward to talking to you guys more. The intuition is, this thing in yellow here is something that we know about, and it's a subject of my talk in July, but I'm happy to talk to that too, but I didn't speak about no metastable states, no nothing here. Thank you.
Maybe we can take one question. We'll start from this side. Yeah, yours?
Yeah, I was trying to get the understanding. So I understand you have a difference between the first and second eigenvalue. In order to observe this effect, then you need the system to be preconditioned to have nothing in this first eigenvalue direction. Is it because otherwise you observe the slow?
In order for the strong Mpemba effect. But in order for the weaker version of it, I need it to be non-monotonic in temperature, sort of kind of like we can talk about it more so that I don't steal from.
Oh no, it's fine.
I'm sorry.
I need some time for setup. I'm sorry.
Yeah, so it's the condition for the Mpemba effect is that there is a non-monotonic dependence on the parameter that I care about, let's say the initial temperature. It could be some other parameter. The condition for its stronger variant, one you care about more, like exponentially faster relaxation, is that it's orthogonal to it, eigenvector.
Can I ask one more question?
Keep it quick.
So would there be, I mean, let's say in a general setting, would there be a theorem that we don't talk about temperatures, we just talk about, we have one Markov chain, we have an initial distribution which has a very bad TVD, total variation distance, with the stationary distribution, and another one which has a much lower. Can this crossing be seen at constant temperature, but with just two initial states? Or is there some theorem that, for example, the TVD, when it is, has a distance at t equals to 0, they must be.
No,
So that would be
example.
Huh?
It's easy to construct a counter example, I think.
No, but this counter example would be a Mpemba effect at constant temperature.
Right.
It would be beautiful if we have that.
Thank you.
Thanks again, Maria.